Good morning. We will continue our discussion about torque on a rectangular current loop in a uniform magnetic field. If you can recall, in the last session we have discussed about a rectangular loop which is placed in a magnetic field B, and the loop was placed in such a way that the area vector was making an angle 90° with the magnetic field, or I can say that the plane of the loop was parallel to the magnetic field. Now today we will consider a case where the area vector makes some angle theta with the magnetic field. So let us say we have a magnetic field B given. So first let me draw the diagram. We have a magnetic field B. This is the magnetic field. And then we are given with a rectangular coil, say PQRS, and the coil is placed in such a way that the area vector A makes some angle theta with the B, means with the magnetic field. So I will draw a coil making some angle with respect to the direction of the magnetic field. Let me say this is the magnetic field, this is the coil which is placed in the magnetic field. So now we will call this magnetic field as B, and then this is the coil, and let us mark the coil as PQRS. PQRS. Let me say the coil have sides A and B. Let us say this side of the coil is A, and the other side of the coil length is B. So as I said, the coil, you can see here the area vector. If I draw, that area vector will make an angle theta with the magnetic field. So let me draw another field over here, and then I'll show you how. So area vector is the vector which we draw perpendicular to the plane of the paper. Now if you draw this area vector somewhere here, so this is area vector A, and this vector, let us say it makes angle theta with the magnetic field. And let the loop carries current I. We can assume any direction. So I'll assume this direction I. We have a rectangular loop carrying current I in the clockwise direction and is placed in a magnetic field. Now what happens here is, when you consider the force on PS, on the sides PS and QR, the two forces will be equal and opposite, but they are collinear, means they lie on the same line and hence they cancel each other. But if you take force on PQ and RS, the force are equal but acting in opposite direction, and then but they are not collinear, and hence they make they give rise to a torque. Now for the detailed explanation about the force, you can refer our previous class. So for the time being, I will write here all this description whatever we have taken. So a rectangular coil PQRS is placed in a uniform magnetic field B, such that a rectangular coil PQRS is placed in a uniform magnetic field B such that the area vector makes an angle theta. Area vector makes an angle theta with the direction of magnetic field. As shown in the figure. Now to find out the forces and then its direction, you can apply Fleming's left hand rule. So that's those for the direction and all, you can refer our previous class notes. Now here the force on arms QR and PS, the force on arms QR and PS of loop are equal, opposite and collinear, and hence they perfectly cancel each other. You can write that point. The force on arms, the force on arms R and PS are equal, opposite and collinear. Thereby perfectly cancel each other. They cancel each other. So if you take force on QR and PQ, it will be like, acting like this. So these forces will be acting in the same line, and they cancel each other. So it will be something like this. The force will be acting equal, opposite, and also they are collinear, and hence they cancel each other. And now when you come to the other part, like PQ and RS, what happens? There will be a force acting on them, and if you once you find out the direction of the force will be opposite to each other. So at this end, if you calculate direction, now we have taken a clockwise direction of the current. So at this end, the direction of the force will be normal to the plane of the paper, and it will be acting in the downward direction, whereas here it will be acting in the upward direction. So it will be something like this. You can mark so here, and also remember the force is perpendicular to the field, so it will be something like this. One force will be acting like this, and the force will be acting something like this. So they will constitute a couple. So now you see here, see how they are acting. So you can see in this picture, so one force is acting in the downward direction, and another force will be acting in the upward direction, in a clockwise direction. So and the other forces being collinear, they cancel each other. So it will be something like this. One force will be acting like this, the other one will be in the downward direction. So those two forces cancel each other, but These two forces will give rise to a couple. So we can write those points, thereby cancel each other. Now here you can write the forces acting on PQ and RS. The forces acting on arms PQ and RS are equal and opposite. Equal and opposite. Are equal and opposite, but not collinear. So they gave rise to a torque. So give rise to a torque on the loop. Now if I draw these two forces, so it will be something like this. So we have A here and then two forces be acting like this. So here this is A. F. F. So the force on arms P, it is PQ, no, sorry, I have written on arm PR, it is not PR, it is PQ. So here it has to be Q, on arm PQ. So we can write force on arm PQ and RS is F is equal to, the magnitude of the force is I, B is the length of the side, into sine 90. So that is equal to IB into B. Now torque will be equal to, so draw a perpendicular distance here. So this angle is theta, because that is what we have assumed. So this angle here, this angle is theta. So this distance will be equal to, this is A theta, so I can write it as A sine theta. Therefore torque is equal to force multiplied by arm of couple. Arm of couple is, in this case it is A sine theta. So this is equal to I B into A sine theta. Now this can be written as IB into, I will write BA together, sine theta. And now this BA can be replaced by A, which is equal to area of the loop, A, which is equal to area of the loop, because A into B, area of the rectangular loop, length into breadth. Therefore we can write torque is equal to IBA sine theta. IBA sin theta. If loop has n turns, or I can write it as I into A into B sin theta. I into A into B sin theta. If loop has n turns, you have to multiply this equation by n. If loop has n turns, multiply that equation by n. And we know I into A. We know m is equal to I into A, where m is magnetic moment. So here m is magnetic moment. I into A is magnetic moment. Therefore torque can be written as mb sin theta, or it is also equal to m cross b. So the torque is given by mb sin theta or m cross b, because m is magnetic moment or magnetic dipole moment of current loop, and the direction is directed in the direction of area vector. M into B is magnetic moment, magnetic dipole moment. So this is the equation for torque, mb sin theta or m cross b. Hope you understood this derivation.